James Webb shows us that the universe could be 2 times as old as previously thought. The proof is faltering, and new hypotheses show that we have made a significant error. So far, the universe isn't 13.8 billion years old at all. It is 26.7 billion years old, or significantly older. The information about the valid age of the universe has fundamentally always been there, but nobody gave the right attention they deserved. The James Webb Space Telescope has been creating a ruckus since it went into operation. Researchers have been excited and stunned since old speculations are suddenly being cleared off the table and new insights are becoming known. With its extraordinary observations of high redshift galaxies, this telescope has given us insights into the youth of the universe that were previously unimaginable. In the process, researchers have found a striking issue: the presence of galaxies that are far more massive and advanced than our current models of cosmology and world development would permit. These observations go against the currently accepted lambda-CDM model that describes the expansion of the universe. The latest discoveries are obvious signs that we have totally misunderstood something. It's possible that our understanding of the central forces and cycles in the universe is not even close to being as full-grown and advanced as we thought. Science needs to reevaluate and is facing an upheaval, one that could change the very foundations of physics itself. At the center of this new science is the long-disregarded work of Swiss cosmologist Fritz Zwicky, a totally new model for the true age of the universe and the peculiarity of the precise development of galaxies. To understand the notable work of individuals like Fritz Zwicky and the new models, we must first go to traditional cosmology. Did you know what an accomplishment of astronomy it was to reproduce the beginning of the universe from numbers and observations? Everything seemed to make sense to such an extent that these assumptions were long believed to be true. The Big Bang marked the start of the universe as we had previously imagined it. This event was when the universe began to expand and cool from a singular and very hot, dense point. The Big Bang laid the foundation for everything that would follow, from the most rudimentary particles to the mightiest galaxies. In the first minutes after the Big Bang, the simplest elements, like hydrogen and helium, were created through processes like nucleosynthesis. After the Big Bang, the universe entered the Dark Ages, a period of several hundred million years during which there were no light sources. Gradually, the universe continued to cool, and the first structures formed under the influence of gravity. Although there were no stars and galaxies, this was a crucial time for the formation of the fundamental building blocks of matter and the astronomical structures that we can still observe today. The era of hydrogen reionization is believed to have started around 400 million years after the Big Bang and lasted until around 1 billion years after the Big Bang. During this time, the first stars and galaxies are said to have formed, whose intense radiation had enough energy to ionize the neutral hydrogen in the intergalactic medium. This process ended the Dark Ages, when the universe became clearer and light could travel greater distances. However, according to the most recent discoveries, these brilliantly shining and highly organized galaxies already existed at this epoch. Shockingly, the studies of the light revealed that these galaxies not only contained very large stars of the first generation, but their composition also pointed to a bright combination of stars of various ages. These galaxies had been in existence for at least several hundred million years when they emitted this light. Researchers had previously assumed that it takes more than 2 or 3 billion years for galaxies of this type to form. But the past standard model of cosmology was based on the assumption that the Big Bang occurred just a few billion years ago. This leads to 3 possibilities. Either the Big Bang happened much earlier, and the universe is far older than 13 billion years, or stars and galaxies formed much faster than previously thought. Or the third possibility suggests we are observing galaxies that may have come from an ancestral universe, or from a universe that exists alongside our own. Let's investigate how scientists have traditionally envisioned the formation of the first galaxies and the evolution of the universe. According to the standard model, galaxy formation coincided with the onset of hydrogen reionization and proceeded as matter in the universe came together under gravity to form larger structures. These early galaxies are thought to have been small, with high star formation rates that filled the universe with light and energy. They are believed to have contained entirely different elements compared to the present-day advanced galaxies. In the previous standard cosmological model, the quasar epoch, APO, was a period that peaked around 2 to 3 billion years after the Big Bang. Quasars are incredibly bright galaxies powered by extremely large black holes that consume matter. Due to their enormous energy and glow, they were the most luminous objects in the still young universe, and they are believed to have played a crucial role in further reionizing and heating the intergalactic medium. But now comes the next sensation. In addition to the incredible galaxies, the James Webb Telescope also found 6 extremely old black holes that existed only a few hundred million years after the Big Bang. The quasar epoch has, therefore, clearly been wrongly dated. According to previous studies, helium reionization took place around 2 to 3 billion years after the Big Bang, following hydrogen reionization, and as indicated, the researchers' past thoughts were set off by the extreme bright radiation of the absolute first enormous stars and quasars. During this time, the already neutral helium in the universe is said to have been converted into ionized structures. This process is said to have proclaimed a further period of warming simplicity. The intriguing thing about this past model of the evolution of our universe is that it was somehow conscious. It checked out, and the objects were few and far between. But James Webb showed the researchers who had long had faith in this hypothesis something totally different: the beginning of a new physics. It's true, the lambda CDM model is now not reasonable, absolutely not, as far as the age of the universe is concerned. Maybe specific pieces of this history of the universe can be valid if we shift them in time later. Perceptions and the requirement for new answers are now making the ways for a new time of physics that will reshape our understanding of cosmic history. First, let's take a look at possibly the biggest source of mistake for cosmologists: redshift and the peculiarity of angular extensions of galaxies. Astronomers have noticed startlingly huge angular extensions in galaxies at higher redshifts. These observations suggest that galaxies might have evolved before and faster than anticipated by the current cosmological lambda CDM model. To understand the precise evolution of galaxies, you can imagine holding a pencil right in front of your eyes. The pencil appears to be a certain size. If you move the pen further away, it seems to get smaller, although the actual size of the pen stays unchanged. The apparent decrease in size of the pen is an example of angular widening. It is a measure of how big or small an object seems depending on its distance. The same principle applies to galaxies in space. A galaxy at a huge distance appears smaller than one that is nearer to us, despite both potentially being of similar size. The angular expansion, therefore, provides us with a clue about how large a galaxy appears in the sky, not how large it actually is. Now, the peculiarity of angular expansion in galaxies and why it's so significant at this point in cosmology: you would expect that as an object like a galaxy gets further and further away, its angular degree gets increasingly smaller. This is true, but only up to a point. At a certain redshift, a measure of distance based on the shift of light to longer wavelengths, we notice an unforeseen defining moment. Rather than continuing to decrease, the angular size of galaxies starts to increase again. This phenomenon indicates that the universe has certain properties of expansion that don't correspond to our past models. It could show that the evolution of the universe is not uniform but has acted in a different way in various epochs. It will be especially interesting if the observed expansion in angular size happens at extremely high redshifts, suggesting that the universe may have expanded differently in the past than we have explained so far with our current cosmological models. Tired light changes all the old computations. This is where the Swiss astronomer Fritz Zwicky becomes an important figure. He was conducting research at around the same time as George Lemaitre and Edwin Hubble. Lemaitre and Hubble are considered the fathers of the Big Bang theory. However, Zwicky was sure that Hubble, at least, made a crucial mistake when he observed distant galaxies. Fritz Zwicky, born in 1898 in Switzerland, later conducted research in the USA and elsewhere. Zwicky demonstrated with his sharp mind, but also caused controversy with his often controversial theories. One of his astounding ideas was the tired light hypothesis, which he introduced in the 1920s and which is now becoming relevant again. Zwicky speculated that the redshift of light from distant galaxies need not necessarily be proof of the expansion of the universe but could rather be explained by the loss of energy of light over vast distances. The redshift of distant galaxies, demonstrating expansion, was popularized by Edwin Hubble. Although Hubble was nearly able to prove his ideas, there were errors that might now come back to haunt him. Hubble's strain showed less than reliable results. Zwicky's hypothesis, on the other hand, explains the peculiarities of extremely distant galaxies without these strains. Zwicky may no longer personally partake in the late victory that may now dawn, but a scientist of modern times could now become a star in the scientific atmosphere. The Indian-born researcher from Canada, Rendra Gupta, combined Zwicky's model of tired light with shifting coupling constants. This led Gupta to an interesting re-evaluation of the age of the universe. Gupta's hypothesis states that major constants such as the speed of light, Planck's constant, and the gravitational constant have not been uniform over time, but have undergone significant variations. This entirely new and dynamic perspective on fundamental constants could explain the observed anomaly in the angular expansion of galaxies and the discrepancies in the current cosmological model. Gupta's work now opens up an intriguing new perspective. If it confirms that our universe is much more complicated and variable than previously thought, Gupta's new computations of the age of our universe arrive at an age of at least 26.7 billion years. Subscribe to the feed now and stay tuned for all new recordings.